All right, so Chapter 4, Section 3 is going to be all application problems involving linear systems and matrices. So in all of these problems, we're going to need to set up some kind of matrix and then use either Excel or our graphing calculator to reduce that matrix and find the solution that we are looking for. So example 1, the Arctic Juice Company makes 3 juice blends, pine orange using 2 quarts pineapple juice and 2 quarts orange juice per gallon, pine kiwi using 3 quarts of pineapple and 1 quart of kiwi juice per gallon, and orange kiwi using 3 quarts of orange juice and 1 quart of kiwi juice per gallon. Each day, the company has 800 quarts of pineapple juice, 650 quarts of orange juice, and 350 quarts of kiwi juice available. How many gallons of each blend should it make each day if it wants to use up all of its supplies? All right, so the first thing we want to do is identify some variables, right? So we need to figure out what is it we're trying to find. That is always the first step in any application problem. So we want to know how many gallons of each blend should it make. So let's let X be pine orange. Let's let Y be pine kiwi. And let's let Z be orange kiwi. And I probably should have been a little bit more specific. When I say X, Y, and Z equals pine orange, pine kiwi, and orange kiwi, what am I really saying? We want X to be the number of gallons, Y to be the number of gallons, and Z the number of gallons. All of these are the number of gallons of each product, right? Because if we just say pine orange, that's not really what it represents. It's the number of gallons of each. Okay, so I like to make tables to help me organize things. This can also be useful in terms of helping us set up things, because tables are really just a different way of saying matrix, right? When you think of a spreadsheet, Excel, or something, when you make a table of values, what you're really doing is just putting it into a spreadsheet or organizing it as such. So I'm going to label my table, so pine orange, pine kiwi, and orange kiwi. And then I need to label what I know about each of these in my columns. So when I look at my pine orange, we see that pine orange is made of pineapple juice and orange juice. So I have pineapple and orange. And the third type of juice is kiwi, right? So for pine orange, how many quarts of pineapple juice am I going to use? 2. How many quarts of orange juice am I going to use? 2. And how many quarts of kiwi juice do I use? There's none in the recipe, so 0, right? Then I go to pine kiwi. Pine kiwi uses 3 quarts of pineapple juice, uses 0 quarts of orange juice, and 1 quart of kiwi juice. We finally get to orange kiwi, and it uses 3 quarts of orange juice, and it uses 1 quart of kiwi juice, and uses 0 quarts of pineapple juice, right? So I labeled them as pine, orange, pine kiwi, and orange kiwi, but we know that we also gave them aliases x, y, and z. So we put the rates in the box. And what I mean by that, when I put 2 in the pineapple column, or in the pineapple row in the orange column, that means for each gallon of pine orange that I make, how many quarts of pineapple am I going to need? 2. So if I make X gallons of pine orange juice, how many quarts of pineapple juice am I going to need? Well, basically what's going to happen is everything in this column is going to get multiplied by X. Everything in this column is going to get multiplied by Y. And everything in my last column is going to get multiplied by Z. So my variables here are going to multiply down to give us the amounts. So there's one more piece of information that I know that I'm going to add to my table over here. And that is my totals. So how much pineapple juice do I have total? 800, right? So each day we have 800 quarts of pineapple juice. How much orange juice do I have every day? 650. And how many quarts of kiwi juice do I have? 350, right? Each row in this table, the way that I've set it up, represents an equation. So notice the way I set this up was on purpose. I put the x's, y's, and z's in here, but if I didn't put the red x, the red x's, the red y's, and the red z's in, that table is exactly my matrix, right? So the matrix that we need to solve is 220, 301, 031, and 800. 650 and 350. And this is a 3x4 matrix, right? So when we're setting up these problems, we should be a little deliberate how we set up our tables, right? Because oftentimes you can take things that would be exactly in a spreadsheet and you already have a matrix that's ready to go, right? So now we need to solve this using any method we wish. So I'm going to just use my calculator. We still have a 3x4 matrix. So we have 2, 3, 0, 800 is row 1. We have 2, 0, 3, 650 is row 2, 0, 1, and 1, and 350 give us row 3. Then we go second math over to RREF. down to RREF, second matrix, choose matrix A, we hit enter, and we get the following reduced row echelon form. So in terms of my table, this is going to be my how much pine orange. So it's going to be 100 gallons of pine orange. Second one, it's going to be 200 gallons of pine kiwi. And 150 gallons of orange kiwi. All right. Let's take a look at our next example. So the key idea in this one, so let's read it first and then we'll talk about it. Traffic is counted as it enters and exits this freeway system. All traffic flows from left to right. Determine the number of cars. Apparently I can't type cars. On each of the 4 roads in the diamond. So the key idea when we have a problem like this, it's what we refer to as a closed system, in the sense of we know the rate in over here is 1,000, and we know the rate out at the other side. And we'll notice, what's 450 plus 350 plus 200? Well, it equals 1,000. So the idea, and the reason I said it's closed, is we don't know exactly what's happening on the inside yet, but we know that the rate in is the same as the rate out. So we can use that information to help us solve this system. So the key idea is at every junction the rate in must equal the rate out. All right, so our goal then is to determine the number of cars on each of the 4 rows in the diamond. So I'm going to label them as X. No, I need to start before that. I need 4 variables. So let's go with W, X, Y, and Z. I mean, you can use any letters you want, but those are the 4 I'm going to pick. So using our key idea, if we were to analyze this junction right here. And remember, we are flowing from left to right. So what would be my rate in at this first junction? So my rate in, well, how many cars are coming into this system? 1,000, right? Has to equal my rate out. Well, at that junction now, what's happening? This should all be in red. Well, at that intersection, it now splits into two different things. How many cars went up and how many cars went down? W went up plus the number of cars that went down, which is X. So these cars can't disappear, right? So the rate in has to equal the rate out. 1,000 cars went in. I don't know how many went up, and I don't know how many went down, but that's why we gave them variables, right? So it's W plus X. All right. Now we want to do the same thing, but let's analyze this intersection. So we want to look at our rate in at that location. So remember, we're still moving from left to right. So there's actually only one road that goes into that intersection. And what is it? W. That's my rate in, has to equal my rate out. Well, what's coming out of that intersection? Well, 450 plus y. Right? Because at that intersection, 450 of them end up here on our way out, and y of them go down. All right. So now let's analyze this intersection right here. What would be my rate in at that point? So who's coming in? Well, as I go from left to right, X is coming in. And what is coming out? Well, I have 200 that are leaving by that bottom path, and some unknown number, Z, which are going up, right? And now finally we get to our last intersection. So coming into this intersection, we have two things that are happening. Who's coming into that intersection? Y and Z, right? So we have Y plus Z, and they have to equal, well, how many cars are leaving the system after that intersection? 350. We now have 4 equations and 4 variables. We can solve this system of equations. So we have a system of 4 equations and 4 unknowns. Before we can write this in a matrix, the system must be in standard form. So remember, standard form is all variables on the left of the equal sign, all constants on the right of the equal sign, right? So our equations are not in that form. So I'm just going to write them all down again here. So we have 1,000 is equal to W plus X. We have W is equal to 450 plus Y. We have X is equal to 200 plus Z. And we have Y plus Z is equal to 350, right? So our first equation, we can just flip-flop everything. So we get X plus W equals 1,000. Our second equation, we're going to minus Y, and that gives us W minus Y is equal to 450. Our third equation, we're going to minus Z, and we get X minus Z equals 200. And our last equation is fine just how it is. So now we have all of our equations in standard form. So we can go ahead and make our matrix. So we have 4 equations and 4 unknowns. So that means we're going to have a 4 by 5 matrix. So 1, 2, 3, 4 rows. And we're going to need 5 columns. So just to be explicit, I'm going to have X, W, X, Y, Z, I'm going to need a little more space, and my constant. I'll make my matrix a little bit bigger. So I look at my first equation, I have 1W, so 1W, 1X, no Y's, no Z's, and my constant is 1,000. I look at my second equation, I have 1W, no X's, negative 1Y, no Z's, and my constant is 450. I look at my third equation, I have 1X, or I have 1X, but I have no W's. No W's, 1X, no Y's, negative 1 Z's, and that's 200. And then my last equation, I have Y plus Z equals 350. So no W's, no X's, 1 Y, 1 Z is equal to 350. All right, so now I need to solve that linear system. Turn on my calculator, go second matrix. We're going to head over to edit, and this time our matrix is a 4 by 5. So 4 by 5. And I have 1, 1, 0, 0, 1,000. I have 1, 0, negative 1, 0, and 450. I have 0, 1, 0, negative 1, 200, and 0, 0, 1, 1, and 350. Alright, and I reduce my matrix to reduced row echelon form. get something that looks like this. All right, so then what does this tell us? It says W plus Z has to be 800. It tells us that X minus Z is equal to 200. And it says Y plus Z is equal to 350. And then our last equation is 0 equals 0. So which is missing the leading one? That's here. So that means Z is going to be our parameter, which we're going to call T. So then we get W is equal to 800 minus T. Our second equation is going to be X is equal to 200 plus T. Our third equation is Y is going to be 350 minus T. And then our last one is our parameter Z equals T. So in this case, we ended up with not a unique solution, but we can further narrow this down because we know that you can't have negative cars, right? So all of these things have to be greater than or equal to 0. So if we take 800 minus T and make it greater than or equal to 0, and add plus T, we know that 800 has to be greater than or equal to T. So that tells us T is less than 800. Okay? Our second one says that this one's not going to be helpful. 200 plus T has to be greater than or equal to 0. So we minus 200, we minus 200. But we actually already knew this, that T can't be negative. So T has to be bigger than 200. Our third equation in Y says 350 minus T has to be greater than or equal to 0. So we add T, and we get T has to be less than or equal to 350. Our last equation would say that Z has to be bigger than 0. So T has to be bigger than 0. So chaining these two things together, 0 is less than or equal to T is less than 350. So we get our solutions are going to be of the form W, X, Y, Z, and our W was 800 minus T. Our X is 200 plus T. Our Y is 350 minus T. And our Z is T. And we know that T has to be between those values, and it would give us all of our solutions. All right. Let's try that again. All right. So a car rental company has 4 locations in the city: southwest, northeast, southeast, and northwest. The northwest location has 20 more cars than it needs. The northeast location has 15 more cars than it needs. The southwest location needs 10 more cars than it has. And the southeast location needs 25 more cars than it has. It costs $10 to have an employee drive a car from northwest to southwest. It costs $20 to drive a car from northwest to southeast. It costs $5 to drive a car from northeast to southwest. And it costs $10 to drive a car from northeast to southeast. If the company will spend $475 rearranging its cars, how many cars will it drive northeast from each of northeast and northwest to How many cars will it drive each of northeast and northwest and northeast to each of northwest and southeast? All right, so let's draw a picture, because I think that's going to be the best way to help us visualize what's going on. We have north, south, east, and west. So let's go ahead and draw. I'm going to use rectangles. So let us start with northwest. And this is going to have too many cars, so this has plus 20 cars, more than it needs. Then we have northeast over here. And the northeast has 15 more cars than it needs. We then have southwest, which is going to be over here. Southwest needs 10 more cars, so it's negative 10 on cars. And southeast needs 25 more cars, so it's at negative 25 cars. So now, let's get to our next set of data. It costs $10 to have an employee drive a car from northwest to southwest. So to go from northwest to southwest, $10. It costs $20 to drive a car from northwest to southeast. So this trip is $20. It costs $5 to drive a car from northeast to southwest. And it costs $10 to drive a car from northeast to southeast. All right. And last sentence. If the company is going to spend a total of $475 rearranging its cars, how many cars will it drive from each of these locations to each of the others? Okay. So we need some variables, right? So what seems like it would be a good variable? What are the things that we have the price per? Well, we know the rate or the price per driving a car from each location, right? So once again, we're going to need some variables. So let's let x be the number of cars from northwest to southwest. Let's let y be the number of cars from northwest to southeast. Let's let z be the number of cars from northeast to southwest. And then we need another variable. Let's let p be the number of cars from northeast to southeast, right? Because we have the possibility of moving a car from either northwest to southwest or southeast, and from northeast to either southwest or southeast. And we want to know about the cost, right? So what's going to be the cost of moving our cars from northwest to southwest? Or let's look at it this way. What's going to be the cost of moving cars to southwest? Well, how many cars does southwest need in total? How many cars is it short? 10, right? So we're going to be moving some number of cars from that location. Okay. And we're going to have to do something similar to the southeast, right? So I want everyone to take a second, and that is not what I meant to push. Let me reshare my screen. Okay, we're back. Well, how many extra cars does it have? Well, northwest has plus 20, right? So it may help if we label each of these. So x is the number of cars from northwest to southwest, so this is x. And then we have let y be the number of cars from northwest to southeast. And we let z be the number of cars from northeast to southwest. And finally, p is over here. Well, so then how many cars are going to be leaving northwest? X and y, right? So what does x plus y have to equal to? So we're going to get x plus y has to equal to the number of surplus cars, which is 20. All right, doing something similar for northeast, what's going on up there? How many surplus cars does northeast have? 15, right? And we have y and p are leaving from northeast, so what does y plus p have to equal? Or z plus p, sorry. So z plus p has to equal to the number of cars that are leaving, which is 15, right? So what else do we know?
Professor Peterson,
Yes, ma'am.
I'm confused why.
All right, so we have two equations, but now we have something similar happening on the receiving end. How many cars is the Southwest going to receive? Well, how many cars are they short? 10. What are the cars that are coming in? Well, that's the red arrow and the green arrow. So that's going to be x plus z should equal the number of cars that they need, which is going to be 10. And then going into southeast, we have blue and purple. So that's going to be y plus p. And how many cars is southeast short? 25, right? Then we have one more equation that we have, which involves the total cost. So the cost in red is $10 per car, so it's going to be 10x plus 20y plus, now our cost in green is 5z, plus our cost in purple, which is going to be 10p. And that's going to have to equal, and how much money were they going to spend total? $475, right? So, writing the system as a matrix, it's going to give us x, y, z, p, and our constants. So we're going to have 1, 1, 0, 0, 20. Zero, 0, 1, 1, 15, 1, 0, 1, 0, 10, and 0, 1, 0, 1, 25. And then our last equation is 10, 25, 10, and 475. So this gives us a 5 by 5 matrix. Let's go ahead and put this into our calculator. So 5 by 5, we have 1, 1, 0, 0, 20, and 0, 0, 1, 1, 15, 1, 0, 1, 0, 10, 0, 1, 0, 1, and 25, and lastly 10, 25, 10, and 475. So we go second matrix over to RREF. And we end up with the following matrix. So this gives us that x is equal to 5, y is 15, z is 5, and p is 10. And then our last equation's all zeros, which is okay because we had x, y, p, and z. So then it tells us that we would move 5 cars from northwest to southwest, 15 cars from northwest to southeast, 5 cars from northeast to southwest, and then lastly 10 cars from northeast to southeast. So we ended up with this row of zeros, and a question that I'd mentioned earlier is oftentimes we'll end up with infinite families of solutions, like what happened in the previous example, and our goal is going to be to minimize something like the cost. So if we come back and we look at this equation right here, this equation guaranteed that we were going to spend $475. Well, the question we might want to ask, is it possible to spend less than $475? And that's a good question, because we had to suppose that we were going to do that by adding that fifth equation. So what if we don't use the fifth equation? So we'll still keep it parked because we know that the cost is going to be 10x plus 20y plus 5z plus 10p. And our goal then would be, can we minimize this? Turns out our answer to that's going to be yes. So if we go back to our matrix, so just to double check, if we grab our matrix A 5 by 5, we'll notice that the cost equation being equal to 475 is the last row. So if we just go into second matrix and we edit it, instead of having 5 rows and 5 columns, we change it to 4 rows and 5 columns. You'll notice that column just disappears. Okay, so now we can come back out here and let's RREF our matrix again. So if we RREF our new matrix A, we're going to end up with the following solution. So this time, we'll notice we don't have ones on the main diagonal. So we have our equation is x minus p has to be -5. Our second equation is y plus p has to be 25. And our third equation is z plus p has to equal to 15. So in this case, once again, we're going to have a parameter in our solution. So in terms of solving for our parameter, we would end up with the following equations, and I'm just going to leave them as p this time. We're going to have -5 plus p. We're going to have y is equal to 25 minus p, and z is 15 minus p. So once again, we'll notice that we are going to get some constraints on this entire thing. So -5 plus p, well, x represents the number of cars. This would suggest that p has to be greater than or equal to 5. Our second equation tells us that p has to be less than or equal to 25, and our third equation tells us p has to be less than or equal to 15. So the first observation we're going to make is that p, whatever it is, has to be between 5 and 15 for our solution to make sense. Writing out our solution, we have negative 5 plus p. We have 25 minus p. We have 15 minus p. And then we have z, or we have p equals p. And then we have our cost equation. Well, if I know my cost is going to be equal to 10 times x, but x is negative 5 plus p. And my next part of the equation is plus 20 times y, which is 25 minus p, plus 5 times z, which is 15 minus p, plus 10p. So now I have my cost equation only in terms of the variable p. So let's go ahead and see what we get. So we get negative 50 plus 10p plus 20 times 25 is going to be 500 minus 20p. 5 times 15 is going to be 75 minus 5p plus 10p. So we get our cost, collecting our like terms. 10 take away 20 is negative 10. Negative 15 plus 10 more is negative 5. And then we collect up our constants. Negative 50 plus 500 is 450, plus 75 is 525. So we know our cost is given by this, and when you look at our slope here is negative 5. So the bigger p is, the lower the cost. Well, we determined up here the largest p-value is p equals to 15. So that tells us that our cost is negative 5 times 15 plus 525 is going to give us negative 75 plus 525 is 450. So the minimum cost is $450, and that will occur when p equals 15. Well, if we use our solution here, it's going to be negative 5 plus p, so negative 5 plus 15, comma, 25 minus 15, and 15 minus 15, and 15. So we simplify, and we get 10, 10, 0, and 15. So that would be x is 10, y is 10, z is 0, and p is 15. So that would be the way to rearrange the cars that would minimize the cost.